Okay, so let's continue to talk about equilibrium, but we're going to be more specific in this video. So we are back to chemical equilibrium constants. We touched on KB, KC, Ka rather. Just briefly scraped on what it is, what to expect. Ka, we said it's an acid that is breaking down into its into the proton and the conjugate base. So you can write an expression that is called Ka, acid dissociation constant. So the A was for the acid. Now Kc, this is an equilibrium constant that is expressed in terms of concentration. So this one is not specific to acids. You can use it for any reaction whatsoever. So Kc, what is Kc? Let's just have a definition. Kc is a constant numerical value for any equilibrium reaction that but is always quoted at a particular temperature. So for any equilibrium reaction, so kuzoti Ka kutova specific kuti for acids, kuzoti Kb kuti for bases. Chaona imenonzi togona kuti Kp whereby we express this equilibrium constant in terms of pressures or partial pressures of a gaseous reaction. So it can have all sorts of names, but the principle really is the same. We want to look at product versus reactants, and it tells you whether your reaction is forward biased or it's backward biased. So let's delve more into this. Okay, so it's important to note here that a Kc is quoted at a specific temperature. So when you're measuring these Kc values, you have to specify the temperature. This is because I want you to note there in bold. This is because only temperature affects the value of Kc. So in other words, you can add or remove reactants and products, change the pressure of the system, or add a catalyst, and the position of the equilibrium will change according to Le-Chatelier's principle, which we discussed in the previous video, to keep Kc a constant value. So Le-Chatelier painenge chichinja iwe ukachinja concentration, Le-Chatelier yo shift position of equilibrium to the right or left. What it's trying to do is to maintain a specific Kc value for that reaction at a specific temperature. So Kc values are constant. This is why we call them equilibrium constants. So these values, once you give a specific temperature, you're going to have a specific Kc value for a specific reaction. And you can alter everything else. Like we are saying, you can change pressure, you can remove products. That is to change the concentration of products. You can remove reactants, whatever you want to change in terms of concentration, reactants or products. You can add a catalyst. You can do all sorts of things. But what this will only do is it will change the position of the equilibrium momentarily, and the equilibrium will re-establish itself at a value which is a constant, which is Kc. Sikainodzoka pa same value. In other words, my concentrations aya anozodzoka futi pangari. This happens at a specific temperature. Why? Because at a specific temperature, your Kc value is a constant. Okay, so ndogo behave my reactions are. It's important for you to remember that. Okay, let's talk about this point here that we said Kc is a concentration term, so can only be used for solutions and gases. You cannot have concentrations of solids, so these are ignored when you're writing Kc expression. We talked about writing Kc expressions in the previous video. So it's important here to note that we are saying my concentrations are solids hatikwanisi kumawana. Saka tinoskipa ma solids when you're writing an expression for Kc. Let's look at that example that is shown there. The following example illustrates Kc expression for homogeneous and heterogeneous equilibria. Homogeneous tinenge tine ma products and ma reactants are in same phase, solid gas or liquid. Heterogeneous anenge akasiyana. So example 1, sulfur dioxide yazokaya plus oxygen, sulfur trioxide. Homogeneous reaction. In other words, all the species have the same phase. So the Kc expression is going to be, I want you to take note again, it's the concentration of sulfur trioxide squared. So you raise the concentration of a particular reagent according to its stoichiometric value. So there's a coefficient of 2 there for SO3. Therefore, we have to square it. We raise the concentration to the power that we have in our stoichiometric equation. So then coefficient iri kuseri kwa-sulfur dioxide ndi2, so we raise the concentration of sulfur dioxide to the power of 2 in the Kc expression times the concentration of oxygen raised to the power of 1. And then my units edu zvekare tofana kuma-calculator according to the same rules. We have to say concentration, which is moles per cubic decimeter, squared for the sulfur dioxide times divided by the concentration in moles per cubic decimeter squared for the sulfur dioxide times moles per cubic decimeter raised to the power of 1 for the oxygen. So tikatamba my units iwawo, we get the correct unit. So that's your expression for Kc there, and the units are moles to the power of -1 cubic decimeters. Okay, and I'll share the rules for calculating the units as I have just illustrated. So tichanatsumatarisha example yechituyo iri kuti, so in this one it's a heterogeneous system. We have calcium carbonate, a solid, to give us calcium oxide, a solid, plus carbon dioxide gas. This is the decomposition of group 2 carbonates, which we'll talk about later on, to give you the metal oxides and carbon dioxide gas. So you can see that we have solids and gases in the same equilibrium mixture there. So if you're asked now to write Kc, you would be tempted to say calcium oxide raised to the power of 1 times carbon dioxide raised to the power of 1 over calcium carbonate raised to the power of 1. Says what I'm going to pana reaction here, sulfur trioxide. But this is not what you do. Why? Because calcium carbonate and calcium oxide are solids, and hence they are not included because their concentrations cannot be determined. So urangaranya kuti ma solids ayo aiswe mu expression ya Kc. This is important. Okay, let's look at something else. Here. So writing Kc expressions, let's continue with that. We have an example here. So we're saying that if you have a general equation such as Wa plus Xp to give us y moles of C and Z moles of D. So another Wx na y na zeta doma coefficients, ma stoichiometric ratios are iwawo. Remember each reactant or each product is raised, the concentration of each reactant or product is raised to the corresponding coefficient in the stoichiometric equation. And so it's going to C and a coefficient of y, so you raise the concentration of C to the power of y. I think it's clear. And you always say your products pamsoro over your reactants. And let's look at an example, another example shown there. Nitrogen, and this would be the Haber process. You can see it's a homogeneous system, everything is gaseous. So Kc is what? Ammonia raised to the power of 2, nitrogen raised to the power of 1 because the coefficient is 1, times your hydrogen raised to the power of 3 because the corresponding coefficient is 3. So when you do that, and then the units, you also have to calculate the units here. And if you calculate well, your units are supposed to be moles to the power -2 dm6. So I'll challenge you to do the calculation of units yourself. However, what do you do when you're calculating units? So you have to remember some general rules of indices, of working with powers. And if something doesn't have a power, it means it's raised to the power of 1. If you have a power in the bottom of a fraction, you can bring it to the top by changing the sign. And it's 1 over moles squared zvakafanana to moles to the power -2. 1 over moles per cubic decimeter zvakafanana to dm cubed. Right, so you have to remember these laws of indices. Anything to the power of 0 is 1. Multiply the numbers. When you multiply the numbers, you add the powers, and you have to remember this. So if you did this well, you're supposed to get the answer that I just shared there. You're supposed to get moles to the power -2 dm6 to the power of 6, +6. So remember, when you multiply, you add the powers. When you divide, you subtract the powers, and it is shown there. Now to find the power of a number, we multiply the powers, isn't it? To find the power of a power, sorry, we multiply the powers. So you have to remember these laws when you're working out the units for KC. Okay, let's talk about this. So KC values and the effects of temperatures. At temperature and baba temperature no change the value of KC. The rest, concentration, pressure, they can shift the position of the equilibrium momentarily, and the according to Le Chatelier's principle, everything will come back, because Le Chatelier's principle will try to minimize the change. So the equilibrium will attain, will re-establish itself such that the value for KC is re-established. Saka zvimwe zvose hazvichinje KC value. The ratios of the products to reactants will be maintained even if you change concentration. But temperature now, temperature will literally change your KC value. It will change. So this is why KC values, they are quoted. You have to quote the temperature at which the KC value was obtained, or else ukasatudza temperature, that value doesn't mean anything. You have to tell us the specific temperature for which a KC value has been determined. Okay, I hope that's clear. So low KC value, since you say concentration of products over concentration of reactants, there must be more reactants than products, so the equilibrium lies to the left. So we can say if you have a low KC, it means that you are generally producing more products than reactants. A high KC value, a low KC value, there must be more reactants than products. When you have a low KC value, it means that the products are fewer than the reactants. So it generally lies to the left. The left side is where you find your reactants. Then when you have a high KC value, it means that you have more products than reactants. Remember, KC is just giving you the ratio of products to reactants. And so this is important to take note. Let's look at this. How the KC value is changed by changes in temperature depends on whether the forward reaction is endothermic or exothermic. We looked at this in the previous video where we said it will depend. If you increase, for example, this is an exothermic reaction, the forward reaction is exothermic, so the backward is endothermic. So what would happen? You have to go back and revise. We said that in this case, if I increase temperature, then I promote the endothermic reaction. So which one is the endothermic reaction? It's the backward. So increasing temperature here will cause the KC value to what? The KC value is going to, we're saying products over reactants, so the KC value is going to decrease. Why is it going to decrease? Because in this case, I will start to form, if I increase temperature, I will start to form nitrogen and hydrogen. In other words, the equilibrium will start to shift to my left, to the production of the reactants. I'm promoting the reversible reaction, which is endothermic. So if I promote the reversible reaction, then what happens? It means that I'm forming more reactants. So if I have more reactants and less of products, then my KC value is going to drop. So you need to see the connection so that you can comment directly to say, if I increase temperature, my KC value is going to decrease. But you have to understand all the connections. So the same goes when I decrease temperature, what happens? I'm going to raise my KC value in this example, which also means that the reaction is going to be lying more to the right. So there's going to be a formation of more product. So this is what you would want. Suppose you were carrying out the Haber process there, you want to try and manufacture ammonia. You would want your reaction to have a forward bias. You want it to have a high KC value so that you produce more of the ammonia. So you can play around with the temperature. Remember, I said those conditions for the Haber process. This is how the optimum temperature is determined. We'll look at the KC values. Which KC value is higher? Remember, KC values are stated against a specific temperature. So which KC value is higher? That becomes our optimum. So you might want to look at that as well. Let's see what else do we have to talk about here. So let's talk about some examples, actual calculations that you can look at here. So that's a reaction between what? Okay, let me check here the reaction that we are looking at. Okay, so we have that reaction which gives us nitrogen dioxide. So this question refers to the following equilibrium system. It's 250 degrees Celsius. The value for Kc is what? 13.7 moles dm to the power minus 3. And in the equilibrium mixture, there's 0.4 moles dm negative 3 of N2O4. Calculate the concentration of nitrogen dioxide in the equilibrium mixture. So you can also play around with the Kc expression to find unknown concentrations. So what's the first step there? Write the expression for Kc. Remember, you have to raise the concentrations to their corresponding powers in the stoichiometric equation. So NO2 squared N2O4 to the power of 1. Then substitute for the values from the question into the equation. We are told that our Kc is 13.7, and in that equilibrium mixture we have 0.4 of what? Of N2O4. When we do our calculations there, we can get the value of your nitrogen dioxide, right, which is 2.34 moles per cubic decimeter. Right, so you have to be able to do that. So I want you to do those practice questions. So we'll continue from here. I want you to write expressions for those and see whether you're able to calculate number 2. So I'll meet with you in the next video. Enjoy your study.